Tesla Full Self-Driving 12.3.6. When full self-driving, supervised, is engaged, the touchscreen displays a visualization of the environment surrounding Model Y, including the roadway and detected objects such as vehicles, pedestrians, curbs, bicyclists, and more. Objects shown in blue represent priorities that full self-driving, supervised, is actively controlling for at a given time. The visualization will also inform you of the system's intended action by displaying a message on the touchscreen, such as when the vehicle is slowly creeping for visibility to take a turn at an intersection. When full self-driving, supervised, also referred to as auto steer on city streets, is engaged, Model Y attempts to drive to your destination by following curves in the road, stopping at and negotiating intersections, making left and right turns, navigating roundabouts, and entering/exiting highways. Unlike traffic-aware cruise control, auto steer, and navigate on autopilot, which are intended for use on multi-lane roadways with clear lane markings, full self-driving, supervised, is meant to work in a variety of driving scenarios. You can use full self-driving, supervised, on any type of roadway, including residential and city streets. Always remember that full self-driving, supervised, does not make Model Y autonomous and requires a fully attentive driver who is ready to take immediate action at all times. While full self-driving, supervised, is engaged, you must monitor your surroundings and other road users at all times. Driver intervention may be required in certain situations, such as on narrow roads with oncoming cars, in construction zones, or while going through complex intersections. For more examples of scenarios in which driver intervention might be required, see limitations and warnings. Full self-driving, supervised, uses inputs from cameras mounted at the front, rear, left, and right of Model Y to build a model of the area surrounding Model Y, see cameras. The full self-driving computer installed in Model Y is designed to use this input, rapidly process neural networks, and make decisions to safely guide you to your destination. Like other autopilot features, full self-driving, supervised, requires a fully attentive driver and will display a series of escalating warnings requiring driver response. You must keep your hands on the steering wheel while full self-driving, supervised, is engaged. In addition, the cabin camera monitors driver attentiveness, see cabin camera. Use full self-driving, supervised, only if you will pay constant attention to the road and be prepared to act immediately, especially around blind corners, crossing intersections, and in narrow driving situations. For more information, see limitations and warnings. At Tesla, we believe that technology can help improve safety. That's why Tesla vehicles are engineered to be the safest cars in the world. We believe the unique combination of passive safety, active safety, and automated driver assistance is crucial for keeping not just Tesla drivers and passengers safe, but all drivers on the road. It's this notion that grounds every decision we make, from the design of our cars, to the software we introduce, to the features we offer every Tesla owner. Model S, Model 3, Model X and Model Y have achieved among the lowest overall probability of injury of any vehicles ever tested by the U.S. government's new car assessment program. Much of this has to do with the rigid, fortified structure of the battery pack that is mounted to the car's floor, which provides a vehicle with exceptional strength, large crumple zones, and a uniquely low center of gravity. Because of their strength, Tesla's battery packs rarely incur serious damage in accidents. And, in the extremely unlikely event that a fire occurs, the state-of-the-art design of our battery packs ensures that its safety system works as intended and isolates a fire to select areas within the battery while simultaneously venting heat away from the passenger cabin and the vehicle. While no car can prevent all accidents, we work every day to try to make them much less likely to occur. Active safety features come standard on all Tesla vehicles made after September 2014 for an added layer of safety beyond the physical structure of each car. Because every Tesla is connected, we're able to use the billions of miles of real-world data from our global fleet, of which more than 9 billion have been driven with autopilot engaged, to understand the different ways accidents happen. We then develop features that can help Tesla drivers mitigate or avoid accidents. Through over-the-air software updates, we're able to introduce safety features and enhancements long after a car has been delivered, as well as release updated versions of existing safety features that take into account the most up-to-date real-world data collected by our fleet. In October 2018, we began voluntarily releasing quarterly safety data in order to provide critical safety information about our vehicles to the public, and in July 2019 we began voluntarily releasing annually updated data about vehicle fires as well. Accident rates among all vehicles on the road can vary from quarter to quarter and can be affected by seasonality, like reduced daylight and inclement weather conditions. Tesla's full self-driving, FSD, system uses neural networks as a fundamental component of its decision-making process. Neural networks are a type of artificial intelligence model inspired by the structure and functioning of the human brain. Here's how Tesla's FSD utilizes neural networks. The vast amount of data collected by Tesla's vehicles, including sensor readings, camera footage, GPS information, and more, is fed into neural networks for processing. Neural networks are capable of automatically extracting relevant features from raw data. In the context of Tesla's FSD, these features could include identifying objects such as vehicles, pedestrians, traffic signs, lane markings, and other elements of the road environment. Neural networks learn from the data they process through a process called training. During training, the neural network adjusts its internal parameters, weights and biases, to minimize the difference between its predictions and the ground truth labels associated with the training data. In the case of FSD, ground truth labels could include information about correct driving actions in various situations. Once trained, the neural network can make predictions or decisions based on new, unseen data. For example, it can predict the trajectory of nearby vehicles, detect potential obstacles in the road, or decide when to change lanes based on traffic conditions. Tesla's FSD system operates in real time, meaning that decisions need to be made quickly to ensure safe and efficient driving. Neural networks are designed to process data and make predictions rapidly, allowing the vehicle to react to changing road conditions in a timely manner. Tesla's neural networks are continually updated and refined over time as more data is collected and as the algorithms are improved. This process, often referred to as iterative learning, allows the system to adapt to new scenarios and improve its performance over time. Overall, neural networks play a crucial role in enabling Tesla's FSD system to perceive its environment, make driving decisions, and navigate autonomously while continually learning and improving its capabilities. Tesla's full self-driving, FSD, system, including its supervised mode, does not fit neatly into the traditional levels of autonomous driving defined by organizations like SAE International. These levels range from Level 0, no automation, to Level 5, full automation, with Level 3 indicating conditional automation, where the vehicle can perform some driving tasks but still requires human intervention under certain conditions. Tesla's FSD system aims to achieve full automation, where the vehicle can drive itself without any human intervention. However, as of my last update, Tesla's FSD system is not yet capable of providing full autonomy, and it still requires human oversight and intervention. Therefore, it does not currently fit the criteria for Level 3 autonomy, as defined by organizations like SAE International. The FSD system is continually evolving through software updates and improvements, and Tesla aims to eventually achieve full autonomy with its vehicles. However, the timeline for reaching this goal is uncertain, and regulatory approval may also be a significant factor in determining when Tesla's vehicles can operate without human intervention. The difference between Level 2 and Level 3 autonomous driving systems lies primarily in the level of human intervention required and the extent to which the system can handle driving tasks. 1. Level 2, Partial Automation. In Level 2 autonomy, the vehicle can control both steering and acceleration/deceleration under certain conditions. However, the driver must remain engaged and be prepared to take over control of the vehicle at any time. Level 2 systems typically include features like adaptive cruise control, lane keeping assistance, and automated parking, but they still require active supervision by the driver. Examples of Level 2 systems include Tesla's autopilot and some advanced driver assistance systems, ADAS, from other manufacturers. 2. Level 3, Conditional Automation. In Level 3 autonomy, the vehicle can handle all aspects of driving under certain conditions or in certain environments. However, the driver must still be prepared to take over control when the system encounters situations it cannot handle. Level 3 systems can operate autonomously in specific scenarios, such as highway driving, but they may require the driver to intervene in more complex situations or when the system requests assistance. Unlike Level 2, where the driver must actively monitor the driving environment, Level 3 allows for more relaxed supervision, as long as the driver is ready to take control when needed. Level 3 autonomy is not yet widely available in consumer vehicles due to technical and regulatory challenges. Some prototypes and research projects have demonstrated Level 3 capabilities, but widespread deployment is still pending regulatory approval and further development. In summary, the key differences between Level 2 and Level 3 autonomous driving systems are the extent of autonomy provided by the vehicle and the level of driver supervision required. Level 2 systems require constant driver attention and intervention, while Level 3 systems offer more autonomous capabilities but still require the driver to be ready to take control when necessary.